Hello, everyone. We're live now. This class uh, specifically is for 5070. You have a paper tomorrow. So I'm going to do a question paper 2-2. It's from May, June, summer 2019. It's a 1 hour, 30-minute question, section A and section B. So you're given, you have to answer all questions in section A. And in section B, you have to answer any three questions. There would be four questions, and you would be asked to answer any of the three questions in that particular section. Let's start with the first question. The first question is it's usually the same question. It's you're given a few substances and you have to answer questions about those substances. Now the first part is which which particle has only 18 protons? So a total of 18 protons. You would have to count the protons. For example, the first one, carbon has a total of six. We'll do the working over here, and let me open very quickly. Open a periodic table. Uh, let's open just 1 second. AQA periodic table. I'll just so here I've opened a periodic table, and I'll have it. And let me rotate this as well. So we have a periodic table in front of us. Let's look at the periodic table and figure out which one has how many. They were asking for 18 protons over here. You have to so carbon over here has six protons. Hydrogen has one proton, so that's one proton into four, so that's equal to 10 protons. So that's not the one. Iron has a lot more protons. If you look at the periodic table, you would notice Fe is over here. Fe is 26. So you can see my point. It's 26. So that's way more than 18. Let's look at H2S. S has a total of 16 protons. It has an atomic number or a proton number of 16. Hydrogen has one proton, and that would be we're going to multiply that by two because I have two hydrogens. So it's going to be an H2S molecule. This molecule is the one that has a total of 18 protons. So that's H2S. Next one is which particle is used to test for a reducing agent. So you need an oxidizing agent because you're testing for a reducing agent. So the other substance must be an oxidizing agent. And you must know that MnO4 ions or KMnO4, they're very good oxidizing agents. And it changes from purple to colorless. Remember that. Just for revision, in the entire O levels chemistry, there are basically two oxidizing agents that you must remember. One is KMnO4. Now this K over here is a spectator ion. It's just potassium plus one, MnO4 is minus one. The other one is potassium dichromate 6. So you must know that these two are your oxidizing agents. Whenever you're being asked to figure out or give the name of an oxidizing agent, just name these two compounds. That's it. Now KMnO4, and also remember about them that the color changes must be known as well. It's going to be purple to colorless. And this one over here is orange to. It changes from orange to green when it reacts as an oxidizing agent. Anyways, MnO4 is the answer. That was just a quick revision, a recap of what of the things that you should know. Next one is which particle is an ion that contains only 10 electrons? So an ion that contains a total of 10 electrons. I think it's this one because N over here has 7 protons. So that means it has 7 electrons. Hydrogen has 1 electron, and that's into 4. So the total electrons are 11. But the entire ion has a plus 1 charge, which means that it lost 1 electron. So if you subtract, it had 11 electrons, but it lost 1 electron. So that leaves you with 10 electrons. So which particle is an ion that contains only 10 electrons? So that would be NH4 plus 1. Let's move to the next page. Now that was a small question. The next page, question number 2. And give me just 1 minute. So now over here, the table shows some of the properties of the elements in group 3 of the periodic table. So group 3 elements, boron, aluminium, gallium, indium, that's Tl, whatever that is, Nh. So the proton numbers are given and the atomic radius are provided and the melting points are also provided. Now, part A of the question, it has not been possible to measure its atomic radius and melting point because it is too radioactive, which means that it decays very quickly and changes into another atom. That is what radioactivity is, that the atom sort of loses particles and changes into another atom. So estimate the atomic radius of NH. NH is over here. So we're going to do an estimate. We're going to follow the trend down the group. What's happening down the group, if you can see over here, what's happening down the group is that as you're moving down the group, uh, the radius is constantly increasing. So that indicates if the radius is constantly increasing, and by a factor of, we just have to give an estimate. So it's 0.125, then 0.125, then 0.150, 0.155. I'm just going to put this at 0.160. That would be an intelligent estimate. So, so 0.160 Newton meters. The other part is explaining using data from the table why it is difficult to estimate the melting point of NH. Why can't you figure out the melting point? The reason is, if you look at the values over here, there is absolutely no trend being shown as you're moving down the group. You can see that the melting and boiling points, they decrease first and then they start to increase again. So there is absolutely no trend being followed over here. So part 2 is explain using data from the table why it is difficult to estimate the melting point of no trend in melting points shown as you go down the group. So absolutely no trend. That's your answer, TK. Absolutely no trend being shown as you're moving down the group. Now the next part is boron has a giant covalent structure. Explain why boron has a high melting point. So whenever you have a giant covalent structure, don't go into a lot of detail. Whenever you have a giant covalent structure, lots of bonds. It's going to have lots of bonds. For example, diamond. Diamond has, it's bonded to 4 carbon atoms. Now that's one giant covalent structure that you have studied. Now boron is not in your course, so you don't really know what the structure of boron is. Anyways, it's now each carbon atom would be bonded to further, it would be bonded further with 4 carbon atoms and so on. And the structure just continues. They're just bonds and bonds. So why do giant covalent structures have high melting points? Um, Large amounts of energy. Energy is needed to break lots and lots of many covalent bonds, many strong covalent bonds. So large amounts of energy needed to break many strong covalent bonds in the giant covalent structure. We'll also quickly check this one with the marking scheme as well. Uh, reason I'm checking it because it was a 1 mark question. There's certain words that carry that 1 mark. So this was, that's exactly what we wrote. It has many strong bonds. This is the part. So large needs lots of energy to break or overcome many bonds. So we're right. We've pointed exactly the words that were needed for getting that 1 mark. Next part is aluminium is produced by the electrolysis of molten aluminium oxide. Aluminium oxide contains Al3 plus and O2 minus. Describe the composition of the electrolyte used in the electrolysis. And you have to figure out name the materials. So it's all about extraction of aluminium. This part. So I'm going to briefly on the right side. I'm going to briefly describe the extraction of aluminium very quickly. So that's just revision. So we're going to revise everything. So extraction of aluminium. First thing, you need to know a few things. Extraction of aluminium, the first thing is, what's the ore? That's bauxite. Bauxite is, it's the raw rock that you mine in from mountains. You mine it. It contains aluminum oxide, but not just aluminum oxides, lots of other impurities, other oxides as well. For example, Fe2O3 and generally other metal oxides. Now, the first part is you need to purify bauxite because you just need aluminum oxide, not the other metal oxides. So, how do you purify bauxite? What you do is you dissolve it in concentrated NaOH. Now, Al2O3, because it's amphoteric, it's an amphoteric oxide. Remember, zinc oxide, lead oxide, and aluminum oxide, they're amphoteric. They can react with acids as well as bases. So now, NaOH is a base. So, aluminum oxide is going to react with NaOH and it will dissolve. And it would form sodium aluminate plus a water molecule. So, Al2O3 dissolves. Simply because it is amphoteric. Other metal oxides don't dissolve because they're basic. Metal oxides are usually basic. So other metal oxides, they don't dissolve as they are basic and they're removed, they're filtered out and are simply filtered off. Anyways, that's the first part. How do you extract aluminum oxide? So we're done with that part. So there are two parts. We have extracted aluminum oxide. The next part is you take that aluminum oxide, pure alumina is electrolyzed then. So what's pure alumina, Al2O3, which has been extracted, is electrolyzed. Now the two things that you do, what you do is you take a container and you put these honeycomb structures in that container. You have this not a honeycomb structure, it's more of a it's more like a comb-like structure. And these are the electrodes that are put. So these are electrodes that are put into the container. So let me color them, shade them as well. Okay, so now it kind of looks more decent. That's the diagram. We can move this to the center as well. Now it looks like a better diagram. This is your anode. This comb-like structure is your anode, and it's made from graphite. So it's connected to the positive terminal of the battery. What does the positive terminal of the battery do? It removes electrons. So it's going to try and remove electrons. That's what the purpose of the positive terminal of the battery is. That it's going to try and remove electrons. And this container is lined with graphite. Now both of them are made from graphite. You have a graphite anode, plus the container is lined with graphite as well. This is connected to the negative terminal of the battery. And what does the negative terminal of the battery do? It starts sending electrons. So it starts to send these electrons. And graphite is a conducting material. It has free moving electrons. So the electrons, it's capable of conducting electricity. Anyways, you add aluminum oxide. Now, when you add aluminum oxide, there are two ions. One is aluminum +3, and it's going to be molten. And oxygen is -2. So the temperature is around 950 degree centigrade. That's kept at 950 degrees centigrade. So the ions can move around. The aluminium ions, the positive ions will be attracted to the negative side, and the negative ions will be attracted to these anodes. So all the O minus 2 ions, they get attracted to this positive anode, and all the Al plus 3 ions, they get attracted to the cathode. So negative is cathode, positive is anode. Anyways, there's one thing that's added into the whole container, and that's cryolite. Now cryolite is Na3Al and F6. The reason it's added is to reduce melting point. So it reduces the melting point of alumina. Why do you need to do that? It saves cost and makes it easy for us to melt aluminum oxide so that electricity could be conducted, and electrolysis is possible now. So cryolite is added, Na3AlF6. Remember that it's probably asked in every paper. Cryolite, you must remember that. What are the reactions that are going to happen? The reactions that happen over here is let's look at the cathode first. Now the battery is sending these electrons. So who's going to gain those electrons? So battery is constantly sending these electrons. So who's going to gain these electrons? You have aluminium plus 3. So the reaction that happens over here is, so the electrons that are coming from the battery they end up being gained by aluminium ions, and they end up forming aluminium metal. So that's how aluminium metal is produced, and that aluminium metal is extracted. It's going to be produced at the bottom, and it will be extracted with pipes and taken out. What's happening on the other side? On the other side, at anode, uh, the battery is trying to remove electrons. So electrons are constantly being removed. Who's the one that's losing electrons? It's oxygen minus 2, and it's diatomic, so it has to be two oxygen ions. They would lose electrons to form oxygen gas molecules. So oxygen gas is being produced. And another reaction that happens over there is that due to the heat, the carbon in graphite starts reacting with the oxygen, starts burning up, and carbon dioxide is also produced. So there are two reactions that are happening at anode. First, oxygen comes over there, negative ion goes to the positive terminal and ends up losing electrons, where it loses electrons and forms oxygen gas, and eventually ends up reacting with the carbon, this comb-like structure, and ends up forming carbon dioxide. Now the thing with this is that the graphite anode it starts to burn up, and it has to be replaced at regular intervals. So this is your entire extraction of aluminium. Sometimes you're going to be asked about the fluorine minus one. There's some more ions that might also be attracted to anode. Remember, anode is not very important because that's not where you're getting aluminium. But due to cryolite, you might have F minus one ions as well. So there might be another reaction that might be happening. If F minus one, they might go to anode, and the battery would pull electrons from it. And it's also diatomic, so I'm going to double that. So it's going to lose two electrons to form fluorine gas. So that is also a possibility. So these are the reactions that happen at anode. At cathode, you only get this reaction. There's sodium ions as well, but sodium ions are very reactive, so they don't like to gain electrons. So if the battery is sending in electrons, it's always going to be the unreactive aluminium ions that would end up gaining electrons. Anyways, that was a quick revision. What we wanted to get this part C. Now, part C was that you had aluminium and it's being produced by electrolysis of. So let's describe the composition of the electrolytes used in this electrolysis. So describe the composition. So it contains pure alumina. We've actually pretty much done everything. So it contains pure alumina, which is Al2O3 molten plus cryolite. And you can give the formula Na3AlF6. The other part is name the material used for the electrodes in this reaction. So we've just done that. It's graphite. Then you have construct the equations for the reaction taking place at the negative electrode, positive electrode. Negative is Al3 plus. Ends up gaining 3 electrons to form aluminium. So it's all written over here. We did a quick revision. So negative side it's Al3 plus. Positive side it's O2 minus. I'm going to just write that down over here as well. So it's going to be O2 minus. 2O2 minus, it's diatomic, loses 4 electrons to form oxygen gas. The next part is now the next part is not about extraction of aluminium. It's about aluminium reacts with. It's about which particle is oxidized. The particle that is oxidized is the one whose charge increases or oxidation state increases. So aluminium goes from 0. It was 0 over here. Now it's +3. So any element whose charge increases, it goes from 0 to +3. That is the one that's getting oxidized. So which particle is oxidized? It's aluminium. Explain your answer. Oxidation state increases. So oxidation state increases from 0 to +3, which indicates that it lost 3 electrons. So anything that loses electrons, that's the substance that gets oxidized. Explain why a piece of aluminum in water does not react. So this is also very frequently asked. Now aluminum is kind of reactive. It's very high in the reactivity series. It's K, Na, Ca, Mg, and then Al. So it's right at the top, next to Ca and Mg. Right after group 2, Ca, Mg, it's Al. So it's kind of reactive, but it doesn't have any reaction with water. The reason is that if you have a piece of aluminum, the top layer is going to get oxidized and it would form aluminium oxide, just like rust in iron. But this aluminium oxide is very unreactive. It's very strong and it's very non-porous. So it kind of protects it. It provides a coating around the aluminium. So it kind of protects it. So a tough, non-porous, and unreactive layer of Al2O3. So a tough, non-porous, unreactive layer of Al2O3 protects aluminium. And it's a 2-mark answer. So let's check the which part is it? It's part E. Let's check the marking scheme as well. Has an oxide layer, which we said it's a layer of aluminum oxide. It's an impermeable coating is impermeable. So I think we answered both parts. That was a tough, non-porous. That's impermeable. So it's pretty much the same thing. And we talked about the layer of Al2O3. Next part is aluminum chloride is a soluble salt. Describe how a pure sample of aluminum chloride crystals can be made from aluminium. So it's a 4-mark question, and it's about preparation of salts. So we're going to just have a quick revision of this. The three methods. Now, there are 3 methods to prepare salts. One is a metal reacting with an acid to produce aluminum chloride. Now I could easily guess what the acid was. It was HCl because you were forming aluminum chloride. So metal plus acid is going to produce hydrogen gas. Now this reaction is you can balance this. Let's quickly try and balance this as well. This should be 2, then this would be 6, and this should be 2 aluminiums and 3 H2. Anyways, this is now a balanced equation. So that's the first reaction. Remember, you're allowed to make salts using the mazet metals. Remember this word, which is mazet. You can't really use all metals because some metals are very unreactive, so they're not going to react with acids. For example, the ones that are lower down, for example, close to hydrogen or below hydrogen, they're not going to react with acids. The reactivity is too low. And then there are metals which are very reactive, so you can't make salts with it. For example, sodium. You can't really put sodium in an acid because you're going to get burned. There's going to be an explosion. So it's going to be a very dangerous process. So you can't use very reactive metals. You can't use very unreactive metals as well. So these metals are right in the middle. It's magnesium, aluminium, zinc, iron, and tin. So these metals, it's safe to produce. They have moderate reactions with acids. So it's kind of safe to produce salts using these metals. Anyways, we could have other reactions as well. The other options that you have are you could use a base like an oxide or a hydroxide reacted with HCl, and it would produce AlCl3 as well, plus a water molecule. So that's another option. And then you have carbonates. You can use carbonates as well. It's going to be Al2 and CO3 thrice plus HCl, and it would also produce AlCl3 plus H2O, but it's going to give off carbon dioxide gas as well. So there would be 3 water and 3 carbon dioxide. Anyways, there are 3 reactions: a metal plus acid, a base plus acid, or a carbonate. Not a base. I mean, these two are both bases. Metal oxide with an acid or a metal hydroxide. You could use aluminium hydroxide as well, or you could use a carbonate. Anyways, I'm going to go with the first reaction. And the first reaction is aluminium with HCl. So I'm going to go with the first reaction. How would I do that reaction? And how would I make? Now they've asked us to prepare a pure sample of aluminium chloride crystals. Remember, we have to make crystals at the end. So I'm going to draw a diagram of what's going to happen. What's going to happen is that you're going to take HCl and you're going to put aluminium metal. Let's say this is a piece of aluminium, like you have these aluminium foils in your kitchen. So you can take a piece and put that in HCl. Now, this is excess method. Remember, whenever a soluble salt, remember the salt that's being produced, whenever you produce a soluble salt, and the reactant, one of the main reactants, the acid is always soluble. It's an insoluble reactant. And you can see that all of these, this is the metal, it's insoluble. Aluminum carbonates, carbonates are all insoluble. Oxides, hydroxides are also insoluble, except for group 1, but this is not group 1. So whenever you have an insoluble reactant and it's producing a soluble salt, the method that's being used is called excess method. What is the excess method? In excess method, remember to add the insoluble reactant in excess. Why do you need to put that in excess? Because aluminium would react with HCl. And HCl would be in smaller amount. So all the HCl would eventually get used up. So you keep adding aluminium. The HCl will react with it, and what would be produced? It would what's going to be produced is aluminium chloride that would become part of the solution, and bubbles of hydrogen gas would be produced, and those bubbles are they're going to escape. So that's not an issue. Remember, we are looking for aluminum chloride salt. Uh, so aluminium, the insoluble reactant, is added in excess so that all the HCl in the solution gets used up. You want the HCl to be used up. Why? Because the solution also contains AlCl3, which is being produced. So you want only one substance in the solution. You want a pure solution. Now, the solution would only contain aluminum chloride if all the HCl gets used up. So you keep adding aluminium. You keep adding aluminium until you stop seeing these bubbles. When you stop seeing these bubbles, that means all the HCl is gone and the reaction has stopped. And this insoluble aluminium can simply be filtered off. Or you can, if you're using a piece of metal, you can simply put your hand in and take it out. So what does your solution contain now? It's pure aluminum chloride. That is all that's present in the solution. So it's pure aluminum chloride. Take it out. So Okay, so coming back, I have to describe this whole process. So I'm going to start writing the answer over here, and it's always the same template that's going to be used. It's always going to be the same template. So what you're going to write is add excess aluminium to HCl and keep adding. We need to get rid of all the HCl. We want the HCl to react completely. So keep adding aluminium until effervescence stops. Which means that if bubbles stop forming, that means the HCl is gone. Now, no more salt and hydrogen gas is being produced, so no more bubbles are seen. So add excess aluminium and keep adding aluminium until effervescence stops. And then once it stops, filter out the excess, the extra aluminium that you had added. Filter out excess aluminium. So the aluminium is gone now. So you have filtered this off. What you've done is you've taken out this piece and you have removed it. So the excess aluminium has been removed. Now your solution only contains aluminum chloride and you have to form crystals. So you have to describe the process of crystallization. It's a 4-mark question, so always describe that process in a lot of detail. So what you're going to do is evaporate the filtrate to saturation point. And then you're going to cool gradually. To obtain large crystals. And the last part would be you once crystals are formed in the solution, you filter out the crystals and dry them in sunlight. Now you could have used any of the equations and the answer would have been identical. Remember, excess method, it's the same template that's going to be used. Always add the excess reactant in excess to the acid, keep adding until effervescence stops. Sometimes effervescence is not given, so you could write that the aluminum remains undissolved because gases are not produced in every reaction. For example, in this base and HCl reaction, oxide and HCl reaction, there is no gas being produced, so there's not going to be any effervescence. So you're going to keep adding aluminum oxide until it remains undissolved. You see it just sitting there at the bottom, and no more is dissolving. That means all the HCl has reacted. So that's excess method for you. And we can so here's what's provided. Use hydrochloric acid. So that was 1 mark. You have to use excess aluminum. That we got 1 mark for that. And then we filter off the excess extra aluminum, and then this is crystallization. Evaporate solution to a point of crystallization, then leave in the sun so that you can dry the crystals as well. So that was all for 1 mark. So we got that 1 mark as well. So that pretty much sums up this question. Now let's move to the next question, which is titanium is a metallic element. So just one physical property of titanium. Now, titanium is a metallic element, but where is titanium? Titanium is over here. If you can see over here, my pointer over here, it's a transition metal. So, what's the one physical property of titanium? Anyways, they said it's metallic, so that indicates that it's going to conduct electricity. So, I'm going to give a description of metallic element. Next part is titanium chloride is a colorless liquid that has a low boiling point, suggests the structure and bonding in TiCl4. So it's covalent, simple covalent. only they have low boiling points. Next one is titanium chloride reacts with water to form hydrochloric acid, and a precipitate of titanium 4 oxide. Construct the equation including state symbols. So titanium 4 chloride, the formula is given. So it's TiCl4. What is it reacting with? It reacts with water, so that's H2O. And what is it forming? It forms hydrochloric acid and a precipitate of titanium 4 oxide. So it's going to be titanium 4 means 4 plus. Oxygen is 2 minus. So if we do crisscross, it's going to be Ti2O4. But remember that when you do crisscross, the ratio must be simple, the simplest ratio. So it's going to be Ti would become 1 and O would be 2. So it's going to be TiO2. Now, part C is titanium is made by reducing TiCl4 using magnesium. Calculate. So this is a moles question now. So we need a calculator for that. Calculate the mass of titanium made from 1,000 grams of TiCl4. So he's also given us the percentage yield. So we're going to break that percentage yield later on. First, this is 1,000 grams. And we need to figure out the mass of this thing. So we need to figure out the mass of titanium. What I'm going to do is I'm going to find the moles of TiCl4. That's the first part. How do I find moles? Moles, the formula of moles is mass divided by the MR. So it's going to be 1,000 grams. And I'm going to divide that by, what's the MR? MR, they've given the atomic mass of titanium, which is 48. And you can have a look at Cl. I don't know why they gave that, because you have a pure table with you. Cl is over here, it's 35. It's given over here, 35.5. So it's 48 plus 35.5, but that's into 4. Anyway, so it's 1,000 divided by, let me take out my calculator quickly. Okay, so it's 48. Okay, so it's 48. You can see this now. Plus it's 35.5. I'm going to put this thing in brackets. Make sure you use brackets. 35.5 multiplied by 4. So the answer that I get is 190. So it's 1,000 divided by 190. So 1,000, and we're going to divide that by 190, and that gives me 5.263. And I'm going to use three significant figures, 5.26 moles. So that's the moles that I'm getting. Anyways, let's move back. Go back to the equation. So I'm getting 5.26 moles of this. So I'm getting 5.26 moles of this. Now the ratio of TiCl4 to Ti is the same. So the moles of Ti are going to be exactly the same as well, 5.26 moles. So according to the ratio, it's 1:1. So I know the moles of Ti, which are coming out to be 5.26 moles. And I need to find the mass. So how do you find the mass? Mass would be, again, the same formula, moles multiplied by MR. So it's 5.26 moles multiplied by the MR, which is given, which is 48. So let's do that. Where's the calculator? 5.26 and multiply that by 48. So I'm getting 252.48. So I'm getting 252.48 grams. Now that's the mass that I get if there is 100% yield. Now the question clearly stated that the reaction has a 90% yield, which means that you're not going to get this 100%. You're going to get 90% of this. So the formula of yield, so you're going to get 90% of this. So I'm going to multiply this by 90% because my output is only 90% of my theoretical value. So it's going to be 90% of that. 90 divided by 100. Multiply that So that is going to be, where's the calculator again? I'm going to multiply this value. So I'm going to multiply this value by zero 0.9, which is 90%. And I get 227.23. So let's round that off to three significant figures, and it's going to give me 227. It's going to give me 227 grams, and we can check with our marking scheme whether that's correct or not. Uh, so it's 227.36, or they gave us 230 grams. So that value is coming out to be correct. One thing that we actually did not do in the previous part was we actually forgot to balance this equation. This equation has to be balanced. We lost marks there. So let's try and balance this equation also quickly. It's TiCl4, so there would be 4 HCl. Cl is balanced. Now H is, so there would be 2 water molecules, and you have oxygen. So this is balanced now. Anyways, let me just recap what we did in this question, in the moles question. TiCl4, that was 1000 grams given. So I found the moles of TiCl4, mass divided by Mr. I got 5.26 moles. And according to the equation, TiCl4 and Ti have the same ratio, which means if this is 5.26 moles, this should be 5.26 moles as well. So the moles of Ti are also coming out to be 5.26 moles, and I multiplied it by the Mr, which gave me the mass of Ti. But then the question specifically stated that the yield was only 90%. So this was the mass if the yield was 100%. So I took 90% of that, and the 90% of this value comes out to be 227 grams. Okay, so I'm going to repeat, before moving to the next page. This is summer 19 question paper 2-2. So summer 19 question paper 2-2. As a next part, question number 4. You're given petroleum, which is an important source of many. Outline the separation of petroleum into fractions such as petrol, diesel, and bitumen. So the first thing, you have to describe fraction distillation of crude oil. I'm just going to quickly just Google an image of fractional distillation of crude oil instead of drawing the whole diagram. So let's find a decent looking image. This one is fine. Okay, this one. I said, what happens? We'll just do working on this image for now, instead of drawing the whole image. What happens is that you have this fractionating column in crude oil. So this fractionating column has at the bottom over here. You can see over here. Crude oil is vaporized. It's vaporized and it has very high temperatures. Now, crude oil is the raw form of oil that's extracted from the ground, usually from the ground, and it is a mixture of many different substances. So many different substances are mixed together in crude oil. So they vaporized at high temperatures. Now, the rule is that at the bottom, uh, as the vapor rises, so as the vapor rises up this column, it cools down. Its temperature starts dropping. It cools down, and when it cools down, at the bottom, substances that have so right at the bottom, substances that have high melting and boiling points, they're going to condense first. They condense first, and the substances that have high melting and boiling points are the ones that are bigger molecules. Remember, that's a rule for organic chemistry, that the bigger the molecule, the higher would be its melting and boiling point. So bigger molecules are going to be found at the bottom. And as the vapor rises, the substances that condense later, they are the ones that have low melting and boiling points. And they are relatively smaller molecules. Now, remember also that in petroleum, smaller molecules are kind of more useful because they burn more easily. So you can see these petrol, high octane petrol, Um and you have these other gases, petrochemical gases. This you probably can't see the whole image right now, but other petrochemical gases can also be found over there. Uh, so as it rises, because different fractions, different molecules have different boiling points. Bigger molecules have more boiling points, higher boiling points. They condense very quickly. Bitumen at the bottom, that's just the residue or the raw form. Then you have these fuel oils, lubricating oils, diesel oils, paraffin, gasoline, and so on. So that's just a brief overview of fractional distillation of crude oil. So let's move back and try and answer this question, which is outline the separation of petroleum. So the first part is it's a 3 mark question, and they've given you a lot of lines. So we're going to answer this first, and we're going to check the marking scheme after this. What were they looking for in this answer? Why did they give us so many lines? So the first thing is crude oil is vaporized at high temperatures. Okay, that's done. It's vaporized. Once it's vaporized, it rises up a fractionating column. So it rises up a fractionating column and cools down. Fractions having high melting points or boiling points, fractions having high boiling points, they condense early as the temperature drops. And substances having low boiling points condense at a much later state. So, and I don't think that should be sufficient. Let me, although I've written a very brief answer, but I think I've covered because we just had to outline it. It was a 3 mark question. So let's kind of check with the marking scheme whether this is a sufficient answer or not. So where's the answer? Just 1 second. Let me end the annotation for a second. Okay, this part. Did we mention the word fractional distillation? That carries 1 mark. So I think, okay, we did not actually mention fractional distillation. We mentioned a fractionating column. Um, the first line I think should have been that was a very obvious line which we forgot. So the first line should have been crude oil is separated using fractional distillation. But even after missing this very obvious line, did we are we still able to get the 3 marks? So we pretty much missed that particular point. Petroleum is heated, it's vaporized. We wrote that. Idea of components fraction with different boiling points. I think we wrote that. We definitely wrote rise up, and we said that having high boiling points they condense early, and substances are having low, so which means that they had different boiling points. So we did answer that. Uh, and the last part, low boiling point come off at the top, high boiling point come off at the bottom. Fractions at different levels. So that is also mentioned. So we were able to get the 3 marks even after missing that first very obvious mark. Fractions having boiling points condense early and substances having low boiling points condense later. So we did mention that. And it was rising up, so that's understood that they obtained higher up. Now, state one large scale use of bitumen. Coming back to the whole fraction distillation thing, remember you have to know all these components. At the top, there are gases which don't condense. So there's methane gas. These are your cooking gases or domestic heating, etc. Then you have naphtha, chemicals. Uh, then you have petroleum or gasoline, for vehicles. You have kerosene, which is for planes, and then you have diesel, which is for heavy transportation like trains and ships. And you have lubricating oils, waxes. You have fuel oil, which is furnaces, especially in power plants. And then you have these bitumen, etc., which is used for roads. So you must know every fraction, what it does, and what's the large scale use. You're going to be asked about this. So large scale use of bitumen, that's for making roads. Next part C, is long chain hydrocarbons can be cracked to produce hydrogen. A long chain hydrocarbon has the molecular formula C12H26. Explain how the formula shows that this hydrocarbon is an alkane. Now the first part. Let me explain the first part. Long chain hydrocarbons can be cracked. That's just for revision. Remember, you have smaller molecules and they're more useful. So you have this crude oil, and you're getting all these molecules. Smaller molecules are more useful. They're more flammable. They burn easily. Bigger molecules, they don't burn very easily. For example, if you try to burn a wax, it burns very slowly. So they're more flammable. What else? They are less viscous, which means they're not thick. They flow very easily. For example, petrol. Petrol is like water, so that flows very easily through pipes. So you want that kind of substances that can flow and not clog your engine or your stoves. So they're less viscous and they have low melting and boiling points, which means they're probably in the form of gases or volatile liquids. Like petrol is a very volatile liquid. So all these are very useful properties. So which is why you crack molecules to obtain smaller molecules. Long chain molecules, bigger molecules are not needed. Anyways, how do you know that this is an alkane? How did we figure out this? Because the general formula of an alkane is CnH2n plus 2. That is the general formula of an alkane. And it fits that. It's C12. H12 into 2 is 24. 24 plus 2 is 26. So it's so you just have to mention it's a 1 mark question. Just mention that it fits the general formula of an alkane. Construct an equation to show the cracking of C12H26 to make hydrogen and at least one alkene. So this large molecule, this large chunk of a molecule, piece of molecule, is going to be broken down in cracking into smaller pieces. So let's make an alkene. Now alkenes have a general formula of CnH2n. So which means if I make an alkene of, let's say, 6 carbon atoms, it's going to be C6H12. I make another alkene of 6 carbon atoms, so it's C6H12. So the molecule has been cracked into 2 pieces. Both of them are alkenes and they're identical alkenes. Now, if you look at the hydrogens, it's 26 hydrogens. So this over here is 12 hydrogens. 12 hydrogens, that's 24. So there must be another H2 gas molecule. So that, now remember, when you're cracking, it could be any small pieces as long as they fit the general formula. So any long chain hydrocarbon that could be broken down into alkenes and a hydrogen gas, as long as 2 things are needed. One is that the formula must be correct. That these formulas over here, they must be correct. They are either a formula of an alkene or a formula of an alkane. The general formulas are with you, so they must fit those general formulas. And the other part is the other third molecule that would be present or can be present is hydrogen gas. Now it's up to you. You could have cracked it in many different ways. What I could have done was I could have cracked it into an alkene with 4 carbon atoms. Then it would be C4H8, and I could have cracked it into an alkene. The other part would be having 8 carbon atoms, so it's C8H16, and my hydrogens would be 24 still. So I would still need hydrogen gas molecules. The other condition is that the sum of all the atoms must be equal to this. So which is why you can add or subtract hydrogens. You can put in hydrogen if your hydrogens are not getting added up. So all the carbons, all the hydrogens, they must add up to the original molecule. So both equations are basically correct. Now the other part is hydrogen and petrol are both used as fuels. State and explain one advantage of using hydrogen rather than petrol as a fuel. Now it's a 2-mark question and they're asking for one advantage. So H2 would burn and produce water molecules. Balance the equation. And water is produced, which is not a pollutant. Now it's obviously not a pollutant. Now they've given you a lot of lines. So you could have talked about petrol. What's wrong with petrol? It burns and produces carbon dioxide. Now carbon dioxide is a greenhouse gas, so that's kind of harmful. It causes global warming, causes the melting of glaciers, and unpredictable weather patterns, rising sea levels. So lots of different problems associated with carbon dioxide. But we'll check the 2 marks. What were they giving those 2 marks for? Okay, so the first one is what is the only product? So it does not lead to. So we actually did mention the greenhouse effect. Uh, so that's fine. There was actually they also gave you that hydrogen is renewable. Petrol is not renewable because it's you get it from ground and it's made after billions of years. Once you run out of petrol, there's no more petrol. So petrol is non-renewable. Hydrogen is renewable. You can get it from water as well. So hydrogen is not a finite resource. There's a lot of water. 70% of the Earth's crust is full of water. So you can get a lot of hydrogen gas. That's not going to be an issue. Anyways, let's move to question number 5, and I'm going to do question number 5 in part 2. So I'm tired of speaking right now, so I'll finish this paper in the evening.